Welcome back to part 5 of the change of variables formula. This time we're going to be looking at what the formula is in 3 dimensions. Okay, so I didn't state all of the assumptions here, but under the assumptions similar to in 1 dimension, so what were they? Well, this time we're going to have a transformation t going from 3 dimensions into 3 dimensions. Okay, we're going to assume that d star in the UVW space is mapped into some sort of region D in the XYZ space. Okay, the technical requirements are we're going to assume that T is 1 to 1 on 2. And another technical requirement is that the Jacobian of t, which I'll define in a second, is never 0 on d star. Okay, so under these situations, the change of variables formula tells us that we can change our variable from the xyz coordinates, integrating over our domain D in the xyz plane, and we can change to the new variables, which we're going to call u, v, and w. We integrate over d star. D star is going to be some sort of new region in the UVW space that is hopefully simpler to describe. Okay, so what is the transformation t tell us? Well, this is going to tell us how to send a point in the UVW space into the XYZ space. So really what we need is we need 3 equations here. Okay, and if we group those into a transformation t, so I didn't write it as formally as in 2 variables, but that's okay. So that's our transformation. Of course, then we need to look at the Jacobian. It's given by the formula over here. Okay, and we've got the absolute values on the outside. We've got the determinant, and then we've got a matrix of partial derivatives. Okay, so this matrix here has all of the partial derivatives of our first transformation x. Remember, that's now a function of UVW. Then I basically put all of the partial derivatives into the first row. And then you can kind of see the formula here, right? Similarly for y, similarly for z. Okay, and remember, there's a lot of theorems about determinants. For example, if I put all of the partial derivatives of the x in the first column, we're going to get the same answer. So depending on which book that you look up, their formula might be a little bit differently, but they're all equivalent. Okay, so remember, it's kind of tongue twister here, but absolute value of the determinant of the matrix of partial derivatives. And then I put in gray the alternative notation. You know, it's okay notation, but it's old-timey. Okay, as always, if you figure out the inverse transformation, instead of figuring out and solving the equations for u, v, and w in terms of x, y, and z, we can use the theorem here that, well, if you've got t inverse, just keep everything in terms of x, y, and z, and do the partial derivatives, and you can kind of see that formula. Okay, so what I'd like to do is really, I'm not going to do any complicated examples here. I just want to prove that cylindrical coordinates give us that the Jacobian is u, and in spherical coordinates that the Jacobian is u squared. Okay, so sorry, u squared sine w. All right, actually, let me just stay here for a second, right? So remember, in spherical coordinates, we use rho, theta, and phi as our three variables, and then the Jacobian was rho squared sine of phi. Okay, so basically if u is taking the place of rho, v is taking the place of theta, and w takes the place of phi, then we need to calculate u squared sine of w. Okay. Similar comments for cylindrical coordinates, right? Where u is going to take r, v is going to be theta, w will take place of z. Okay, so let's go ahead and just start and again, so I'm just going to do the Jacobian calculation here. So the Jacobian of this transformation t, remember this is t right here. Okay, we want the absolute value of this. Actually, let's just do it without the absolute value. Let's just calculate the Jacobian. All right, so this is the determinant. Now I'm going to have a 3 by 3 matrix where I need to do, so the partial derivative of the x's. So I've got three variables, x, u, v, w. Okay, so I like using color here. So we've got u, v, w. Okay, and then t sends these into the variables x, y, z. Okay, so it kind of helps to not use z twice. Again, I'm using w equals z, but okay. So we're going to do x, xu, xv, xw, yu, yv, yw, and then finally zu, zv, zw. Okay, so determinant, let's start doing partial derivatives. So the partial derivative, let's do the first row. Okay, partial derivative of x with respect to u, cosine of v. Partial derivative of x with respect to v, negative u sine of v. Partial derivative of x with respect to w, 0. Okay, let's now look at the next row. Now let's do the partial derivatives of y with respect to u, v, w. Okay, partial derivative of y with respect to u, sine v. Partial derivative of y with respect to v, u cosine of v. And finally, partial derivative of y with respect to w, 0. And my favorite one to calculate, the last one, still three partial derivatives, but we're going to get partial derivative of z with respect to u, 0. Partial derivative of z with respect to v, also 0. Partial derivative of z with respect to w, we've got 1. Okay, so how do we calculate 3 by 3 determinants? Okay, so this part I have to review. Really, there's many different ways of calculating them, but what I'm going to do is I'm going to expand by the last row. Okay, and what we do in determinants, we have to remember this kind of checkerboard pattern of pluses and minuses. So remember when we did the cross product, we had plus, minus, plus along the top row. Okay, and then you basically do this alternating pluses and minuses. So if I go along the first column, I've got plus, minus, plus. And now that I know that I have a plus on the, the last row here, then I'm going to have plus, minus, plus. And I guess for completeness, I'll do that. Okay. So now that we've got that, what I've got here then is to do the determinant, we do, it's called the cofactor expansion. We're going to do this number times the determinant of the matrix that we get when we cross out these rows. So I've got the determinant of this, and sorry for all the plus minuses, but we're going to get 0 because I've got a 0 in front. Okay, but I'm just kind of going to do this first one nice and slow here. Okay, then we're going to have a plus a negative 1 times 0. And now I expand along this. So to do that, I'm going to cross out the last row and cross out the middle column. So this gives me a determinant of okay, of that 2 by 2 matrix. Okay, then the last calculation here. Again, both of these are just going to be 0 because I got the 0 in front, so let me just wipe them out. But the last one has a plus 1, so we'll do plus 1, and times the determinant of, okay, so what determinant? Cross these out, grab this 2 by 2 matrix. Okay, sorry, the pluses and minuses are bugging me, at least on these. Okay, cool. So this gives us, oops, sorry, our final form here where we're going to do the determinant of this 2 by 2 matrix. So we've got 1 in front times cosine of v times a u times another cosine of v. So I've got u cosine of v squared minus a negative. So minus minus becomes plus u and then sine squared v. All right, so notice that the u factors out, but then I'm left with cosine squared v plus sine squared v. And as always, time to make Pythagoras happy. We know, due to his theorem and his identity, that is 1, giving us u, which is what we were trying to prove. Okay, so we got u, and take a quick check. Remember, we are treating u as our r, and it's exactly what the Jacobian looks like in polar and cylindrical coordinates. Okay, sweet. Now the tougher example. Spherical coordinates is next, but let me actually grab some of this since some of this info is exactly the same, so I don't have to write it again. So I find this pretty helpful here. Okay, so again, we've got our transformation t is given by these equations here. And let's go row by row. So let's start by calculating the partial derivatives with respect to the 3 different variables. Okay, let me zoom in because I do need to write neat and small here. 3 by 3. So first one, partial derivative of x with respect to u. Okay, so that's going to give me sine w cosine v. Partial derivative of x with respect to v. Okay, so take the derivative of cosine of v, that's negative sine v. The rest is going to stay unchanged. All right, and finally we need the partial derivative of x with respect to w. So w is in the middle here, so we're going to have cosine of w, and then the rest stays unchanged. So it's going to be u cosine of w cosine of v. Okay, and sometimes what I like to do when we've got a big matrix is I like to put what I call these little brackets here just to help me kind of visualize and just kind of keep everything separate. Okay, so let me close this matrix now that I'm... Okay, so next up, let's go to the equations for y and calculate all of the different partial derivatives. Okay, so the partial derivative of y with respect to u, sine w sine v. Partial derivative of y with respect to v, u sine w, cosine of v. Partial derivative of y with respect to w, u cosine of w, times sine of v. Okay, and moving on to the next row. Okay, what do we have? So the partial derivative of z with respect to u, cosine w. Partial derivative of z with respect to v, 0. Partial derivative of z with respect to w, negative u sine w. All right. So just like the last example, we can expand this along any direction. So the way I'm going to do it is, let's pick the one, let's expand along the last row because it has a 0. Okay, and that means follow the checkerboard pattern. That means we've got these signs to account. Okay, so the determinant is, so we're going to expand along, let me use these 3 numbers here. Okay, and keep in mind that when we expand along the middle one, that one will be 0. So let me start by saying, okay, the first one we're going to have cosine of w with a plus times the determinant of a 2 by 2 matrix, where, which one? Well, we cross out these 2 rows. So, giving me this 2 by 2 matrix. Okay, then we're going to have minus 0 times the determinant of, let me just put a star here. Okay, what is going to be that matrix? Well, cross out the last row and cross out the middle column. So we do have this column and this column to put in there. That's going to be star. However, I'm not going to write it because we know we're going to get 0. Okay, that means we have one more piece to keep track of. So we got plus a negative u sine of w. Okay, and then we've got another 2 by 2 determinant. So this time I will write it. So we're going to cross this out, and I will copy the 2 by 2 matrix that I get, put it over here. Can get rid of this little extra minus sign that isn't there. Cool. All right, again, this is 0, so just keep track of that. All right, let's put the little guide lines here and calculate some 2 by 2 determinants. So the first one's going to be that times that minus this times this. And the second one, same Same idea here. So cosine of w, big parentheses. Okay, so when I multiply these things, what are we going to get? I'm going to get a negative u squared. I've got sine w, and there's no other sine w, so it's just going to be sine w. Sine v, but there's two of those, so sine squared v. And cosine of w. Again, since we're multiplying here, the order doesn't really matter. Just keep track. Let's check our work, right? Negative u squared, sine w, sine v squared, cosine w. Okay, that looks correct. Then we're going to subtract the product of the off diagonal, so another u squared, sine w. There's no other sine w, but then there is a cosine of v squared, cosine squared v, and then cosine of w. All right, next up, I'm going to have negative u sine of w, parentheses. Actually, I'm gonna have to write this down below. And okay, another cross product. I'm sorry, another determinant. So let's start by doing sine of w times cosine of v times u times sine of w cosine of v. So we've got just a single u, sine squared w, cosine squared of v. Okay, minus a negative, so it's minus minus, so that's plus. 1u, I've got a sine squared w, sine squared v. Okay, so let's continue with this example here. We've got so let's zoom in a little bit. What is common? So I'm going to look at this part right now. What can we factor out that is the same in both of these expressions? So we've got a u squared, actually a negative u squared. I can pull that out. Both of them also have a sine of w. Both of them have a cosine of w. Okay, so actually a lot in common. So I already have a cosine of w in front, so I'm going to pull out a minus u squared, sine of w, cosine of w. But again, there's already a cosine of w in front, so it's going to be cosine of squared of w. Parentheses, what's left over is sine squared v, because I pulled out the minus sign, plus cosine squared v. That's great. Pythagoras identity is going to simplify that to 1 in the next step. Okay, then looking at the next expression, grab another color. Let's look at this and factor out all of the common pieces. So I've got a u from both of them and a sine squared of w from both of them. So I will factor this out. Now, what do we have in front? We already have a minus u sine of w, so that's going to be minus u. So I already have a u, so when I pull out another u, I've got u squared. Okay, I've got sine of w, so it's going to be sine of w cubed. Okay, and then what do we have left? So parentheses, cosine squared of v plus sine squared of v. Okay, another chance to make Pythagoras happy. These are going to simplify to 1, so what do we have next? Negative u squared, sine of w, cosine squared w, times 1 minus u squared sine cubed of w times 1. Okay, so what pulls out over here is, let's factor out a minus u squared. Okay, what else is common to both of them? Looks like one copy of sine is common to both of them. So what I have left over is cosine squared w. Okay, I pulled out the minus u, so then this is a plus. And I pulled out one copy of sine, so I'm left with a sine squared of w. Okay, time to make Pythagoras happy again. So he is jumping for joy, all of the uses of his theorem. Okay, so at this point, we've got negative u squared sine of w, which is the Jacobian. Okay, so you're asking, oh, well, why do we have this minus sign? Well, remember, this is kind of a more subtle calculation from the determinants. That's telling us essentially the orientation, which is basically how we are going around the boundary and in what specific order. But remember, in the change of variables theorem, hold on, if the last example got a smiley face, this deserves a smiley face. Okay, so let me finish my thought here. So going back to the change of variables formula, right? So this is kind of showing us why we need those absolute values, because we're really just keeping track of just volumes. We're not keeping track of orientation, or basically how we are moving through the solid here. That is a much more subtle conversation that you explore in future courses. Okay, cool. So again, I'm not going to do a calculation. I think at this point you are well equipped to do those on your own, but it's very satisfying to prove the change of variables formulas in cylindrical and spherical. So I didn't need that extra space. So for the last thing, I just want to kind of end the little series on just kind of this abstract notation that we call push forwards and pull backs. So this is language that we use in differential geometry. And okay, so we began this long series on essentially change of variables. And remember, the first change of variables formula you probably remember was the u substitution. And we call this a push forward, okay? And you can kind of read the example I have written here. It's a simple example from Calc 1. I want to just talk about the language here, right? So what the idea is, when we set up this new variable u, really we're saying u is some function of g that we recognize, and then the du has its derivative. Now, the thinking is, well, when we rewrite the integral in terms of the new variables, okay, what we're saying is we essentially start in x. These are, I always call these the blue variables. When we use this function g, think of g as essentially pushing the information about x forward to new variables in u. Okay, this is where the name push forward comes from, right? We say that the g pushes the information about x forward to the new variable u. Okay, now there's another side to this little picture here. There's function phi. What is that? So for that, this is a pullback. Okay, and what's a pullback? I've got an example where I'm calling it the trig sub, where essentially we start off with an integral, and the substitutions are x equals tangent of theta. So we're kind of going to a new variable theta, but the theta is kind of inside of a function, right? So kind of x is by itself, and I've got some function of the new variable. So the thinking here is, it's like the variable, so I'm going to call it s to not confuse it with theta, and just kind of speak generically, right? So we've got essentially with these types of transformations, there is another function, let's call it phi, and dx is the derivative of this phi with respect to s. Now, the hint is, okay, right, so x equals 0, x equals 1 in the last example, right? We use g to push that information forward to u. The way we use the x information, we actually have to use the inverse of the transformation. So in this example, it's the function is tangent, so we use inverse tangent. Or more theoretically, we can say this is just inverse of phi. Okay, so this is why we need those technical requirements, right? Where we say it's 1-to-1 and onto, so that this is possible. Okay, so because I'm using these inverse mappings, this is where it gets its name of a pullback, right? I'm pulling back information on x via this function phi backwards to the s variable. Okay, so eventually we do change the integrals into the new variables, okay? But the new variables are now s, and conceptually, right, because we're going to be using phi inverse, we are essentially going backwards in this arrow. And yeah, for that reason, we think of the phi pulling back the information about x into the new variable s. Cool. Well, thank you so much for watching all of the videos to the end here. A massive series, but I hope this info pushes you forward into your more advanced coursework. Thank you. See you next time.